In this mini presentation, we use a simple story about a suspicious die to understand hypothesis testing. By the end, you should know what the null hypothesis is, what the alternative is, what a p-value is, and what type 1 and type 2 errors mean in plain language. Here we anchor everything in a story. You are not doing abstract math. You are investigating whether your friend is cheating. The key data will be the number of 6s out of 60 rolls. That will be our test statistic. Now we translate the story into math. The parameter p is the true chance of rolling a 6 with your friend's die. The null hypothesis says p equals 1/6. The alternative says p is larger than 1/6. This is our official way of saying, I suspect your die is tilted towards 6. Here we model the number of 6s with a binomial distribution. If the die is fair, the average number of 6s in the long run is 10 out of 60. Randomness means sometimes more, sometimes fewer, but 10 is the center of the distribution. Alpha is your tolerance for false alarms. If alpha is 5%, you are saying, I accept that in the long run, 5% of fair dice will be wrongly accused by this procedure. In your quest for the truth, you must accept some risk of type 1 error, but you can put a cap on it. That's your significance level. Now we turn alpha into a concrete rule. We calculate how many 6s would be so many that we almost never see them with a fair die. 16 or more 6s out of 60 has only about a 3.4% chance under fairness, so that becomes our trigger for calling the die suspicious. The p-value is a measure for how surprising the observed result is under the assumption that null is true. To calculate it, we temporarily assume the die is fair and ask, what is the probability of getting this result or something more extreme in the direction of the alternative? Small p means, wow, that would almost never happen with a fair die, so the fairness story looks doubtful. 12 6s out of 60 sounds like a lot, but under a fair die it is actually quite common. A p-value of 29% is way bigger than our 5% cutoff, so we simply say, this is within the range of normal random luck. No cheating verdict today. Note that we don't accept the fairness story either. We do not apologize. We were entitled to test the die, and we did. Now we can keep playing. "18 6s out of 60 is a very different story. Under fairness, this has less than a 1% chance, so the fairness assumption looks very shaky. Here the p-value is less than 1%, so we reject the null and statistically accuse the die, and maybe the friend. Type 1 error is the false alarm. You yell, this die is loaded, even though it was fine all along. Our choice of alpha, like 5%, roughly controls how often that embarrassing situation happens in the long run. You cannot set this risk to 0, because if you do, the probability of type 2 error explodes and you will never catch a cheat. Type 2 error is the opposite mistake. You say, everything looks fair, even though the die really is biased. Power is the probability you catch a cheating die when it is cheating. In this story, about 76% of loaded dice with p equal 0.3 would be caught by this test. More rolls means more information. With 6 rolls, 3 sixes could just be luck. With 600 rolls, 186s would be a huge red flag. Bigger samples let you keep the same alpha while improving your chances of catching real cheating. Here we connect the dots. Everything in hypothesis testing, from the null to the p-value, shows up naturally in this die example. Once you understand it for dice, it is the same logic for drugs, machines, or any real-world study you will see later. This quote is a reminder that there is always a trade-off. If you want a tiny chance of false alarm and a huge chance of catching real effects, you have to pay with large samples, which means time, money, or effort. Statistics is basically negotiating a good deal between risk and resources.